Okay, let's continue and let's see the code of the Prim's algorithm. And well, let me warn you first, and this is not a easy algorithm. Well, to understand that it's not easy, and when we want to analyze this code, and it's even harder. Okay, so well, to make the things easier, let me explain two of the important parts. So the number one, well, for the key. So for each of the node, and we will have a key, and the key means the cost to connect a node to the spanning tree. Okay, so when we connect a node, say when we connect C to the spanning tree, and then the cost is 9, right? Because we have to connect the C to the B so that C is connected to the remaining part of the MST, and then the cost to connect C is a 9, okay? So that is the key. And then we have the pi, and then we have used that pi before, and that is the parent. So if we use this one again, so we can say, well, B is the parent of C because C is going to be C is going to connect to the remaining part of the MST by connecting to B. So B is a parent of C. So those are the important parts. And then, well, before I read the code line by line to you, and let's just use this one as example. So we want to generate the MST using this one, this graph, and we have to specify where do we want to start. So we want to start from here in this node, and then we call this R. Okay, and the very first step, if you see the first three lines of code, so for each of the node, and we specify the key is infinity, and then we set the pi to be nil. Okay, and then for the pi, well, another thing I want to remind you is instead of showing you what are the values in the pi, and then I will just use the red edges to show the references to the parents. Okay, so this is the first step after running the first three lines of code, and we will have the infinities as the key, and then for the first value, so which is the start point of this prim algorithm, and we will set that to be a 0, saying, well, to connect this node to the MST, and the cost will be 0 because this will be the start point of the MST. And the next part is, well, we will change the color to be red, saying, well, we want this to be removed. So when we are doing later, when we are doing the extract min, and then we don't want to consider the red nodes, so we are saying the red vertices have been removed from the queue. Okay, so well, for now this red node won't be considered as part of the queue anymore. And after that, well, we are going to try to visit all the adjacent nodes. So for the adjacent node 3, and then now we are going to update the key to be 3, and this means, well, if we want to connect the 3 to the MST, and then the cost will be 3 because we can connect this node to the U, and in this case, by doing that, and we are spending a 3 as the cost so that this node is connected to the MST, right? So the same thing for this one. So since this node is also connected to U, and then this node can be connected to the MST with a cost of 14. Okay, so now we have figured out the cost of connecting those two nodes to the MST, and the cost will be 14 and the 3. Okay, and the next part, well, this is the tricky part. So you see, we want to do a extract min, and we want to extract the min from all the blue nodes, not all the nodes, because the red nodes are detached from the queue. So we want to find the minimum from the blue nodes. So we are going to move the U to 3 by doing the extract min. And after that, we want to do the same thing. We want to find the neighbors of the U, and then we want to check. We want to tell them they can be connected to the MST, or if they are already connected to the MST, we want to update the cost if that's possible. Okay, so we're going to start from the easy part, which is it here. So for this node, Now it can be connected to the MST with the cost of 8. So I'm gonna connect this to the MST, and then I'm gonna update the key to be 8. And here is a tricky part. So for the 14, this node is already connected to the MST. And what is the cost? The cost is 14, right? Okay, so but for here I have another edge, and then the cost is 10. What does this mean? So originally this node is connected to the MST, but the cost is 14. Now I can offer you another chance to lower your cost, and still you are connected to the MST. And the cost is, well, the way is I can use this path instead of the path of 14, right? So in this case, I'm going to update the red edge, and then I'm going to update the value from the 14 to 10. Okay, so that's it for the next step. And then we want to do another round of the extract min, and then the minimum will be the 8, right? So we want to connect the neighbors if they're not connected to the MST, or if some of the neighbors are already connected to the MST, and then we want to update the key or update the cost. Okay, so for this one, I want to update this because now it can be connected to the MST, and the cost is 2. And the same thing for this one, and the cost for you to connect to MST will be 15. And I guess that's it. And I want to do another extract min, and another extract min will move us to here, which is 2. And for the 2, and then I can update the neighbors of the 2. And for this one, 9 can be connected to the MST, and then the cost is it's 9. And then this node can be connected to the MST, the cost is 4. And ta-da, for the 10. Okay, so originally this node is connected to the MST, and then the cost is 10. And now an even better offer. The offer is if you want to take this edge, and then the cost will be down to 5. So I want to update this edge, saying for this node, if I want to connect to the MST, I want to take this edge from now on. So I want to update this one, and then the cost of connecting this node to the MST will be 5 now. Okay, so if I want to move on and extract min, and then I will have this one. So this is a 4, right? And then for this 5, it is already connected to the MST, and if I want to take this one, and the cost will be higher, so I won't bother to update that. And the next one, I'm gonna check 5, and then there's nothing more to update, and then 9, and then 15. Okay, so this is the process of doing the Prim's algorithm. And what we have been doing is, well, we start from a node, and then we want to expand my MST. Okay, and then eventually we will end up with a MST, a minimum spanning tree. We are keeping part of the edges from the graph, and then we get a tree structure, and we have all the nodes connected. Okay, so this is the Prim's algorithm. And the next part, how often is the extract min called? So think about that. So when was the first call? The first call was we take this one, right? So well, this is the first call, and then for each of the extract min, we will visit one more node and one more node. So if there are a total of n nodes, and then we will run the extract min for n times. Or if we say the number of the vertices is v, and then we will run the extract min for a total of v times. Okay, so well, what will the running time be? Well, the running time depends on the queue. So well, it really depends on how we implement the queue, and then the queue is really a X factor of the Prim algorithm, because the performance of the queue will also impact this part, extract the min, and there will be even more things we have to discuss. Okay, so let me give you the answer first. The answer is, well, if we are using the binary heap as the queue, and then the time complexity will be the O E log V. Okay, so how do we get that? well for this slice, and then I want to show you. So for the blue inks, well, they show the defined time complexity of the Prim's algorithm, and then I use the black characters to show you, since we are using the binary heap, and then there are some additional tasks or the hidden tasks in this case. Okay, so first box. So for the first box, we are going to visit all the vertices. So well, that is the OV for sure. And then if we want to create a queue, well, a priority queue or a heap, and then well, I should well, remember, it should be a min heap. Okay, so if you want to build a min heap, and then what is the time complexity? Well, because we are doing the min heap, because later we are going to do extract min a lot, and then by doing a min heap and then finding the minimum will take the constant time, right? So in this case, we do want to build a min heap, not a max heap. And if you want to review the lecture of the heap sort, and then you will see, to build a heap of the v nodes, and then the time complexity will be the OV. So anyhow, the defined time complexity is the OV, and then the hidden task to build a min heap, the time complexity is another OV. So for the first box, and then the time complexity is a OV. Okay, and for the second box, that's the easiest. Well, there are just two lines of the code, and they're both primitive steps. So the second box, 01. Okay, and the next one. So well, how many times we are going to do the extract min? And we know that, and that is the v. If we have v vertices, and then we are going to run that for v times. Okay, and the next part, well, how do we do the extract min? So if we have a min heap, and then we want to take out the minimum, I'm not saying find the minimum. I'm saying we want to find the minimum and then take it out. So in this case, by taking that out, we do have to fix the heap structure again, right? So to fix the heap structure, and that is a O log V. Okay, so that is, well, for this part, for this iteration. So this iteration itself is a OV. However, for the extract the min heap, that is a O log V. Okay, so well, this extract min, since we are doing a min heap, and there is a hidden cost or a hidden task, that is to fix up the heap again, so that is a log V. So for the third box, that is a OV log V. Okay, and then the last part. So for the last part, well, if I ask you, well, how many edges we are gonna visit, and what is your answer? So this is a undirected graph, right? So we have a total of e edges, and then for this part, for this for loop, how many edges we are going to visit in total? And then you will say there are e, but actually there are 2e. So the reason is, if there is an edge between A and B, and then in the A's adjacent list, and we will see the edge AB, and then in the B's adjacent list, and we are going to see the BA. So in this case, well, there will be a 2e, because for each of the edge, we will visit that twice, right? So for this for loop, it is guaranteed that we will visit that for the 2e time. So that is the O2e. Okay, so the next part here is a hidden task again. So remember, when we are updating the key, we may reduce the key to a even smaller value, right? So if we go back here, so originally this node is 14, and then we reduce it to 10, and then we reduce that to 5. So this means it is possible for us to reduce the value of a key, and then that key itself is in the min heap. So when we are reducing the key of a node in the min heap, and then we may violate the property of a min heap. So what do? We have to fix the heap again, right? So to fix a heap, and then there is a O log V time. So in this case, and then there is indeed a O log V here. So if you want to multiply this together, and then you will have the O E log V. Okay, so we have a OV here, we have a constant time here, we have a V log V here, and then we have a O E log V here. So if we want to add all of them together, and then if we are assuming that E is the number of the edges is, well, at least equals to or higher than the number of the vertices. So we will have the V log V and E log V, and then constant time, or the V, we pick the most significant part, and then what do we have? We will keep this one. So that is the O E log V, and that is the time complexity of the Prim's algorithm. So this is not an easy algorithm, and then, well, if you don't want to read the whole chapter of this book, so in the chapter 23, and there is a long paragraph discussing the time complexity of the Prim's algorithm, and I definitely recommend you to take a look on that paragraph, just that paragraph. Okay, so, well, here are two interesting questions. Well, just now we just analyzed the Prim's algorithm, assuming that we are using the min heap, right? How about if we keep the keys in a linked list? And if that is a linked list, and what will be some of the hidden tasks, and then we are considering the hidden task, and what will be the time complexity of the Prim's algorithm. So think about that. Those two are very interesting questions. Okay, so, well, that's it for today, and I will see you on Thursday. Okay, bye.